Okay, so let's go ahead and multiply and divide with rational expressions. And one thing we'll actually see with dividing is that we're going to be doing something called rationalizing denominators. So before we get to that, we actually have to see how to multiply radical expressions. And so a lot of this is going to be kind of similar to what you see with variables, because we're going to be foiling some things out and distributing. And one thing we need to see first is one thing that we saw 2 sections ago. And that was the fact that when we multiply 2 radicals together, and remember they have to have the same index, so let's put an n for both of these, then we're just going to multiply the stuff on the inside, and so we get the nth root of a times b. So let's go ahead and look at some examples. We're told to multiply. And just like with anything we do in math, it's implied that we should always simplify our answer. So some of these we might be simplifying a little bit. So number 1 here, we're given the square root of 10 times, in parentheses, 4 plus the square root of 7. Now, first thing we want to do here is multiply. And so in this one, we're going to be distributing. So if we go ahead and distribute here, we have the square root of 10 times 4. Now, if you notice, this 4 is not in a square root. So think of this kind of like if we had x times 4, this would be 4x. We're going to do the same thing with radicals. We're just going to put that any numbers that don't have a radical out in front, and then keep the square root of 10. Next, we're going to go ahead and multiply the square root of 10 times the square root of 7. They're positive, so I'll keep the plus sign. And we're going to multiply the things on the inside. So 10 times 7 is 70, so square root of 70. Now you always want to make sure that you can't simplify down. So if we look at the square root of 70, remember our goal is to find a perfect square that goes into it. So 70, we have 1 and 70, 2 and 35, 3 doesn't go into it, 4 doesn't go into it, 5 goes into it, and it's going to go into it 14 times. 6 doesn't go into it, but 7 does 10 times, and that's it for our factors of 70. Now notice that none of these other than 1 are perfect squares, which means we cannot simplify this. So this is our final answer. Let's go ahead and try another one. So number 2, we're given 3 parentheses, square root of 20 plus the square root of 45. Now I'm going to go ahead and distribute first. You could technically simplify now, but there's some cases where if you simplify now and then you multiply it by another radical, you may have to simplify again. So I would just always simplify at the end. So if we distribute here, again, this 3 isn't in a square root, so it's just going to go out in front of each of these. So 3 times the square root of 20 is 3 square root of 20. 3 times the square root of 45 is plus 3 square root of 45. And now if we look at simplifying these down, the square root of 20, well, 20 can be split into 4 times 5. So I'm going to go ahead, keep that 3 out in front, and let's split 20 into 4 times 5. In the second one, 45 can be broken down into 9 times 5. And now if we go ahead and look at what we have inside the square root, we have the square root of 4, which is 2, so we'll take that out. And the square root of 9 is 3, so that'll come out in front. And remember, when you bring it out in front, you're going to multiply by what's already out in front of the radical. So in this case, we're going to multiply the 3 by the 2 that we're taking out. So we're going to have a 6 square root of 5, because that's what's left inside the radical. And now we're taking out a 3, so we're going to have 3 times 3, which is 9 square root of 5. And now there is one last thing we can do here. These are both square root of 5. So we can go ahead and add these coefficients. So we get 15 square root of 5. So kind of similar to variables. When you distribute with variables, you want to make sure you combine your like terms. Same thing here, we're going to combine our like radicals. Okay, so number 3, let's go ahead and try another one of these. This one we're given in parentheses 3 square root of u plus square root of v times 3 square root of u minus the square root of v. Now, these are something special called conjugates. And so what conjugates are, I'll write this over here. Conjugates are where you have the same terms. So see how we have a 3 square root of u, 3 square root of u. We have a square root of v and a square root of v, and one is a plus and one is a minus. So there's something special that happens when we have conjugates, and that's what we're going to use when we rationalize denominators in a second. So let's go ahead and see what happens when we multiply these. All right, so we have 2 terms in each. So we're actually going to FOIL this out. So we'll multiply our first terms first. And when we do this, we have a 3 squared of u times 3 squared of u. So doing this, we're going to multiply the 3. So 3 times 3 is 9. So you multiply the outside part. And then we're going to multiply the radicals. So square root of u times the square root of u. Well, if we did this, remember if we multiply what's on the inside, so u times u is u squared. The square root of u squared is just u, because you remember the square root and the square cancel out. So this is a special property. If you have the square root of u times the square root of u, you just get u. So you get whatever's on the inside. So if we had, let's say, the square root of, say, x to the 4th times the square root of x to the 4th, we get what's on the inside, so we just get x to the 4th. So instead of having to go through this middle step here, I'm going to skip that and go straight to the final answer. So we just get a u. Now, if we go ahead and do our outside terms, we have 3 times a negative 1. So I'm going to write that in there. We get negative 3. Square root of u times the square root of v. Those are not the same, so we're just going to multiply what's on the inside. We get the square root of u times v, or uv. And now the inside terms here, again, we have 1 times 3, which is positive 3. And then we have v times u, which, again, they're not the same term, so we can't just get rid of the square root. We have the square root of uv. I'm switching around the order so that it's in alphabetical order. And then we have our last terms here. So again, multiply the stuff in the front. So 1 times negative 1 is negative 1. Square root of v times square root of v, again, using our shortcut here, is just a v. Now, if we go ahead and look at what we have here, what like terms do we have? Well, if you look at our terms in the middle, these are opposites of each other. Even though there's a bunch of stuff going on here, we have a square root, we have a u and a v. They are opposites, so they actually cancel out. And so we're just left with 9u minus 1v, or minus v. So that one was kind of tricky. That's about as hard as those conjugates are going to get. But this over here, I'm going to put a few stars here. This shortcut is really helpful to know. So we're going to use that a lot when we're looking at rationalizing denominators. Okay, so let's go ahead and do a few more of these. Let's go ahead and do number 4. Number 4, we're given in parentheses the square root of x plus the square root of y times the square root of x minus the square root of y. So again, we have conjugates here. So the outside and the inside terms, that's where these guys came from, should cancel out. Let's go ahead and FOIL it all out though. So we have the square root of x times the square root of x. Now that is our shortcut here. So square root of x times square root of x is x. Outside terms, square root of x times a negative square root of y. Well, positive times a negative is going to be a negative. Square root of x times square root of y is the square root of x, y. The inside terms, we have the square root of y times the square root of x. That's positive. And we have y times x, which again, I'll leave as x, y. And now for our last terms, we have the square root of y times the square root of y. One is positive, one is negative, so we'll get a negative. And the square roots cancel out, so we just get a y. Now, again, we had conjugates, so we should have these middle two terms canceling out, which they do because they're opposites. So we just get x minus y. And notice how in both of these we didn't have any radicals in our final answer. That is another important thing that we'll see in rationalizing denominators. All right, so let's go ahead and try one more of these before we get to rationalizing denominators. This was number 5. Number 5 here, we're given the square root of 13 minus 2 squared. So first thing we want to notice here is that we have some quantity being squared. And one thing hopefully you'll remember from Math 95 is that we can't just square each one of these terms. We want to remember that squaring something means multiplying it by itself. So we're going to take the square root of 13 minus 2 and multiply it by the square root of 13 minus 2. And now it is just like what we were just doing. So first things first, let's go ahead and FOIL. So first terms, we have square root of 13 times the square root of 13 is 13. That's our shortcut. Outside, square root of 13 times negative 2. Well, this 2 isn't inside the square root, so I'm going to leave that negative 2 out in front of the square root of 13. The inside, these are exactly the same as what we just had. So we have negative 2 square root of 13. And lastly, negative 2 times negative 2 is a positive 4, so plus 4. Now, be careful when you're simplifying this one. If you look at the middle terms here, we have a negative 2 square root of 13 and a negative 2 square root of 13. Even though those are the same, they are not opposites, so they do not cancel out. So we do want to go ahead and actually add those together. So negative 2 minus 2 is negative 4 square root of 13. And then lastly, we have 13 plus 4, which is a positive 17. And so you can do it in this order if you switched it around. So let's say the 17 was first and then the minus 4 square root of 13. That is also perfectly fine. Remember that you cannot just subtract these numbers in the front. Think of it like terms. If we had 17 minus 4x, you wouldn't combine them because the first term doesn't have an x. Same thing here. The 17 does not have a square root of 13 with it, so we cannot combine those. All right, now let's start talking about rationalizing denominators, and this is where the dividing radical expressions comes into play. Okay, so rationalizing denominators basically means that we're going to get rid of any radicals in the denominator. That's kind of one of the, as you can call it, a rule with radicals, is that you do not want any radicals in the denominator. Just like we saw this last time, or in section 10.3, we also don't want any fractions under a radical, because that means that there's a radical in the denominator. So they kind of go hand in hand. So one thing, and this is what we're going to be using to rationalize denominators, is the fact that if you take a number, divide it by itself, you always get 1. And this is true even if we had x divided by x, we get 1. And if we have the square root of 2 over the square root of 2, this is still 1. And if we multiply something by 1, it does not change. Oops. The value of an expression. So like if we had 3x times 1, well, any number variable times 1 is still itself. So we're going to be using this fact to get rid of radicals. And the last thing we're going to be using is the fact that a radical times itself, so root 2 times root 2, remember our shortcut, this gets rid of the radical and we just get a 2. So we're going to get rid of the radicals by multiplying the radical by itself in most cases. And we're going to multiply something, the expression, by a form of 1 so that we don't actually change the value. So let's go ahead and just jump into some examples. We're told to rationalize the denominator. Now, it should tell you to rationalize the denominator in all of your questions in the homework. If it just says simplify, it's still implied that we have to get the radical out of the denominator, and you have to do that by rationalizing. So number 1 here, we'll start off with one that's pretty nice. We're given 8 over the square root of 3. Now, for this one, the only thing we can do to simplify is to get the radical out of the denominator, because we don't like to have radicals in the denominator. The denominator should always be whole numbers because it tells us how many pieces we have in the whole. If you think back to like basic definition of a fraction, so like 1/4 tells you have 4 pieces in the whole. If we have a radical down there, we can't really have 1.5 pieces in a whole. So what we're going to do is we're going to multiply this by a fancy form of 1. And to get rid of the radical, we're going to multiply it by the square root of 3 over the square root of 3. So we're multiplying it by 1. It's not changing the value of it. But by multiplying by the radical that you have in the denominator, so it should always match what you have down here, except for the case where we have addition and subtraction, and we'll check that out in the next section of examples. That's where conjugates will come into play. This should always get rid of the radical, and it won't change the value. It'll change how it looks, but it will not change the value. So if we go ahead and multiply across the top, 8 times the square root of 3, well, 8 is not inside a radical, so it's just going to stay out in front. We get 8 square root of 3. On the bottom, square root of 3 times square root of 3 is 3. That's why it's really nice to know that shortcut without having to actually multiply this out. If we did multiply it out, square root of 3 times square root of 3 is the square root of 9, which we know is 3. So you can always go through that kind of longer route of doing this, but I would recommend just kind of memorizing that nice shortcut. And so this one is now done. Sometimes you'll be able to reduce the numbers out in front, not inside the radical. Sometimes you'll be able to simplify the radical and take things out of there. And we'll see some like that in a second, but for this one, there's nothing we can do. So let's go ahead and try another. This one, we're given 9 square root of 7 over the square root of 3. So for this one, the thing to keep in mind here is that I don't care if there are radicals in the numerator. If you think back to our little circle fraction picture, let's think of fourths. Let's say I had 1.5 fourths. It's perfectly okay to have 1.5 or some kind of fraction or decimal on the top, because I can shade in 1.5 fourths, but I cannot have a fractional number of pieces in the whole, because all of these pieces are whole pieces. So anytime you have a radical in the numerator, you're just going to kind of ignore it. And we only care about the one that's in the denominator. So we're going to multiply by the square root of 3 over the square root of 3. Again, it won't always be 3's. Now, if we go ahead and multiply straight across, on the top, the 9 is outside of the radical, and that's the only number. There's technically a 1 here, but 9 times 1 is still 9. Leave that out in front. The square root of 7 times the square root of 3. 7 times 3 is 21, so we have the square root of 21 over square root of 3 times square root of 3 is 3. Now, there is something we can do to simplify this one. If we look at the radical first, 21, we have 1 and 21, 3 and 7. There's no way to find a perfect square that goes into 21, so that's not something we can do. But we can reduce the 3 and the 9. Anytime it's multiplication, there's no addition there, we can reduce. So 3 goes into 3 one time, 3 goes into 9 3 times. So the denominator is just a 1. We don't care about a 1 in the denominator. So we're just left with 3 square root of 21. Okay, let's go ahead and try some more. Next one here, we're given 3 over the square root of 48. Now, for this one, again, same thing, we want to rationalize. And there are technically 2 ways of doing this. We could go straight into rationalizing. So this is the way that they do not show on MyMathLab. So if you were to click on the question help, it won't go through this way, because this way is sometimes a little bit longer. But I do want to show you because instinct sometimes kicks in and you want to just go straight to rationalizing. And so this is how you do it that way. Then I'll show you the other way, where we're actually going to simplify first and then rationalize. So for this one, first thing we're going to do is rationalize. So we're going to multiply by the square root of 48 over the square root of 48. Multiply across the top. So 3 times the square root of 48 is just 3 square root of 48. And then what are we going to get on the bottom? Square root of 48 times square root of 48 is 48. One thing to notice is that this 48 is in the square root. This one on the bottom is not. You cannot cancel them out because they don't have the same value. The square root of 48 is a lot smaller than just 48. So keep that in mind. Don't get in the habit of kind of trying to cancel those out. What we can do, though, is we can simplify 48 and break it into a perfect square and another number. So I'm going to go ahead and go through the factors of 48. So we have 1 and 48, 2 and 24. We don't have any perfect squares yet. 3 goes into it 16 times. And 16 is a perfect square. So this has to be our largest perfect square because all these other numbers, they're just getting smaller from here. So I'm going to break that 48 into 3 times 16. Keep the bottom the same. And now the square root of 16 is 4. So I'm going to go ahead and take that 4 out. And remember, you multiply it by what's in front. So we're going to have 3 times 4, which is 12. And then we're left with a 3 on the inside over 48. Now there's one last thing we can do to simplify. We can go ahead and reduce the 12 and the 48. 12 goes into 12 one time. 12 goes into 48 4 times. So we're left with 1 square root of 3, or square root of 3, over 4. So this is one way of going through this. Just rationalizing first. Sometimes your numbers will end up pretty big if you do it this way, because you're going to be multiplying by 48 in this case. If we had had like a square root of 10 up here, you would have had to do 10 times 48, and then you'd get some really big numbers to try to simplify. So this other way is the way I'd recommend, so that you work with smaller numbers. I'm going to star this one. So starting off with the same thing, first thing I'm going to do is simplify the bottom. So I'm going to leave that 3 up top. And now we're going to go ahead and simplify the bottom, just like we did up here, actually. So we're going to break that 48 into 3 times 16. And we'll take out that square root of 16 as a 4. So we're going to have 3 over 4 square root of 3. Now you should already notice that the numbers are a little bit smaller. Now if we go ahead and rationalize, again, don't cancel out these 3's. One is in a square root, one is not. When you rationalize, you only have to multiply by the radical, as long as there's no addition or subtraction, because we'll still see that case. We don't need to multiply by this 4. That 4 is just going to make our numbers bigger, and they're going to get reduced back down anyway. So if we go ahead and just multiply by the square root of 3 over the square root of 3, there's a lot of square root of 3's in this one. Across the top, we're going to have 3 times the square root of 3, so 3 root 3. On the bottom, now this 4 is a whole number. There's no radical around it, so I'm going to leave that. And then we have the square root of 3 times the square root of 3. That is 3. Now you do have to remember to multiply that by the 4 that was out in front. So I'm going to go ahead and simplify that right now. So 3 root 3. You should also notice something that we could do here, but I'll multiply and then we'll do that. So 4 times 3 is 12. Now if we reduce, notice how the numbers are similar to what we have up here, but smaller. 3 goes into 3 one time, 3 goes into 12 4 times. Same answer, but you get to work with smaller numbers. Sometimes there might be an extra step. I think here we had, so this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. They're about the same. So I would definitely simplify first, if you remember to. If not, it's still possible the other way. You just might be working with larger numbers. Okay, now let's go ahead and try 2 more of these. Number 4, we're given negative square root, and there's a fraction under here, 8 over 45. Now, one thing to keep in mind here is that we do not like fractions under the radical, because if there's a fraction under the radical, that means that the denominator is under a radical sign, which obviously we don't want because that's what we've been trying to get rid of. So first thing we want to do is use our quotient rule with radicals and split this up. So I'll leave that negative out in front. That's just going to kind of hang out the whole time. And then on top, we're going to have the square root of 8. On the bottom, we have the square root of 45. Before I start rationalizing, because if we were to rationalize right now, this is such a really good example for this. Don't write this part down. If we were going to rationalize, we would multiply by the radical on the bottom, and we'd have to do 8 times 45. That's going to be a pretty big number that I don't want to deal with. Instead of doing that, let's simplify first. So let's go ahead, leave that negative out in front. 8 we can break down into 2 times 4. 45, perfect square that goes into 45 is 9, so 9 times 5. Again, bringing over that negative. Now we can take out the square root of 4, which is 2. So we'll bring out a 2. We're left with a square root of 2 on top. On the bottom, we can take out the square root of 9, which is 3. We're left with a 5 on the inside. Now, there's nothing to simplify down right now, but we can go ahead and now rationalize by the square root of 5. So we can multiply by a smaller number than that 45 we would have had to multiply by in the beginning. Again, keep the negative in the front because we're still multiplying by a positive number. Now on the top, this 2 is the only whole number out in front, or 2 times 1, which is 2. And then square root of 2 times square root of 5, we multiply, so square root of 10. And on the bottom, we have 3 times square root of 5 times square root of 5 is 5. So just don't forget to multiply that 5 by the 3 that was already out in front. Now, if I simplify, we have, again, negative. 10 cannot be broken into a perfect square. So we're going to leave this as 2 square root of 10 over 3 times 5, which is 15. Do not be tempted to reduce the 10 and the 15. And why is that? 10 has a radical, 15 does not. So they are not, this is not a normal 10, this is the square root of 10, which is a smaller number than the actual 10. All right, now this last one is a little weird. These don't come up a whole lot. I think there's only one in your homework, which is why I wanted to include it. So this one we're given the 4th root of a fraction of 81 over y. Now, first thing we're going to do is simplify it just like we did in number 4. So I'm going to break it up. We have the 4th root of 81 over the 4th root of y. Now, y is just a single y, so we can't do anything with that right now. We'll have to rationalize. With the 4th root of 81, one number times itself 4 times gives us 81. This would be 3. So I'm going to switch that out with a 3 so we don't have to deal with that one anymore. But now we have a 4th root of y on the bottom. So one thing to keep in mind here is that if I were just to multiply by the 4th root of y, these do not cancel out because this would give us the 4th root of y squared. So the 4th root and the squared don't cancel out. So let me erase that. What we want is we need the 4th root of y to the 4th, because then the 4th root and the 4th power would cancel and we would just have a y. That's what we've been using up here. We've been using the fact that square root of 3 gives us the square root of 3 squared. Now, if we look at this one, we already have one y inside our radical expression here. We need 4 of them. So we're going to multiply by the 4th root of y cubed. And I'm going to kind of write this out in extra steps just so you guys can see this because this is kind of a weird one. If we look at the top, this 3 is just going to go out in front. So 3 4th root of y cubed. On the bottom, we're going to have the 4th root. Now, if I actually multiply these, y times y cubed, we add the exponents, we get y to the 4th. And we do get what we want. So the 4th root and the 4th power do cancel. So we have 3 4th root of y cubed over y. So you're going to multiply in general by 1 less than the index. So if this were the 5th root of y, we would have multiplied by the 5th root of y to the 4th. So 1, your exponent should be 1 less than your index. Or in other words, because depending on what they give you to start off with, that doesn't always work. Your exponents on these y's, so y to the 1st, y cubed, should add up to the index. All right, but you should just see one of those on your homework. They're not super common. Okay, so now let's go ahead and take a look at one of the last things here. We're still rationalizing, but now we're going to be rationalizing denominators with binomials. All right, so hopefully you remember that binomials are polynomials, so we have x's and numbers that have two terms. So in our previous examples, we had single terms on the bottom. There was no addition or subtraction. In these ones, we're going to have binomials. And so what we're going to use is something called the conjugate. Let me write this better. So conjugate. And so what the conjugate is, and this is something we saw when we were multiplying actually in the beginning of this section, is when you have the same terms with the opposite sign in the middle of them. So let's say we had a 1 plus the square root of 2. Well, the conjugate would be 1 minus the square root of 2. If we had the square root of x minus the square root of y, well, this one's already negative, so we're going to flip it and it becomes the square root of x plus the square root of y. And one last example, because this one sometimes throws people off. If we have negative square root of 3 plus the square root of 2, we're still only changing the sign in the middle. So this is going to become negative square root of 3 minus the square root of 2. So only change the sign in the middle. All right, so let's go ahead and look at some examples. We're again told to rationalize the denominator. So number 1, we're given negative 4 over the square root of 5 plus 2. So for this one, first of all, notice that we have a radical in the denominator. We don't want that. But we also have addition in the denominator, which we didn't see before. So what we're going to do is we're going to go ahead and multiply by the conjugate. And so just like before, when we multiply something, we don't want to change the value. So we're going to multiply it by a fancy form of 1. So the conjugate of our denominator is the square root of 5 minus 2. We're going to do that on the top and on the bottom. And then anytime you're working with addition or subtraction, I would always put everything in parentheses. Even if you don't necessarily need them, I will always add in the parentheses just in case. Because on the top, what we want to do here is we want to distribute. And then on the bottom, we're going to be foiling this out. So let's go ahead and look at the top first. Negative 4 times the square root of 5. Well, that's negative 4 square root of 5. Negative 4 times negative 2 is positive 8. On the bottom, we have the square root of 5 times the square root of 5. We've done this enough to know that this is 5. Remember, those square roots cancel. Then we have the square root of 5 times negative 2. That 2 is not in a square root, so the -2 goes out in front of the square root of 5. In the middle, we have 2 times the square root of 5. That's a +2 square root of 5. You should notice something when you're doing this. And then 2 times -2 is -4. Be careful with your signs. It's really easy to kind of miss the minus sign in between. So what you should notice is on the bottom here, our middle terms are the same, but with opposite signs. So those should always cancel out. So let's go ahead and cross those guys out and simplify a little bit on the top. So, well, nothing to do on the top right now because these are not like terms. And on the bottom, we have 5 minus 4, which is 1. But any number or expression divided by 1 is just the same thing. So let's get rid of that denominator. And this is our final answer. The tough thing for this one is just that arithmetic we're going to be doing. But with practice, it's not too bad. So let's go ahead and try another one. This one we're given the square root of 3 plus the square root of 5 over the square root of 2 minus the square root of 7. Now for this one, notice that we have radicals on both the top and the bottom, but where do we not care about the radicals? Well, we don't care if they're on the top. That's perfectly fine. I only care about the ones in the denominator, so we're going to multiply by the conjugate of the denominator. And in this case, the conjugate is going to change this minus to a plus. So we're going to have the square root of 2 plus the square root of 7 on the top and on the bottom here. If you ever multiply by something, let's say you accidentally multiply by the conjugate of the top, that would get rid of the radicals on the top, but not on the bottom. And remember, our goal is to get rid of the radicals in the denominator. If that doesn't happen, go back and check your arithmetic. Make sure you multiplied by the correct thing, which I would not have because this is a 7, not a 2. So always make sure you're kind of double checking that you're ending up with what you wanted to end up with. Okay, so I threw in the parentheses around all of those. Let's go ahead and start foiling. Let me erase these marks so I have room. All right, so we're gonna have square root of 3 times the square root of 2. So that's the square root of 6. Then we have the square root of 3 times the square root of 7. That is a positive square root of 21. Square root of 5 times the square root of 2 is the square root of 10, positive. And lastly, the square root of 5 times the square root of 7 is the square root, positive, of 35. Those are all kind of different square roots, so there might not be much simplifying, but we will check at the end. Now on the bottom, there is a kind of shortcut, but I don't recommend doing the shortcut and kind of skipping steps, just in case you're multiplying by the wrong thing. So I'll mention it, but I'm not ever going to do it in practice here. Okay, so square root of 2 times square root of 2 is 2. Whoops. Square root of 2 times the square root of 7 is the square root of 14, positive. The inside terms, we have the square root of 7 times the square root of 2, but it's a negative times a positive. So negative square root of 14. And then lastly, we have a negative times a positive, so negative square root of 7 times square root of 7 is 7. Now, the thing I want to point out here is that notice how these square root of 14s came from the outside and the inside. Those will always be the ones that cancel out. So if you wanted to skip multiplying those, you could. But again, I don't recommend it just in case you're multiplying by the wrong thing. If you fully multiply it out, you'll notice your mistake. So I'd recommend always multiplying the full thing out. All right, let's combine some like terms. or simplify radicals. On top, we have a 6, which cannot be broken down into perfect squares because we only have 1 and 6 or 2 and 3. 21, again, it's either 1 and 21 or 3 and 7, not perfect squares. Same thing with 10, 1 and 10 or 2 and 5. And 35 is either 1 and 35 or 5 and 7. So I'm actually going to have to leave all of these square roots up on top. On the bottom, these guys cancel, and 2 minus 7 is negative 5. We're going to leave it just like this, since the top cannot be simplified. All right, let's try one more of these before we take a look at simplifying 2 expressions. So number 3, I believe, yeah. All right, number 3, we're given 2 over the square root of k plus 3 square root of z. All right, so we have radicals in the denominator that we want to get rid of. So we're going to multiply by the conjugate of the denominator, change the plus to a minus, so square root of k minus 3 square root of z, square root of k minus 3 square root of z. Throw in your parentheses. And then we can go ahead and start multiplying. So on the top, we have a single term times a binomial, so we will just distribute. So 2 times the square root of k is 2 square root of k. Now we have 2 times negative 3 square root of z. So 2 times negative 3 is negative 6, then square root of z. On the bottom, we can FOIL, so square root of k times square root of k is k. Square root of k times negative 3 square root of z. Now, this one's kind of ugly, but we have a negative 3 coefficient, and that is our only coefficient, so we'll bring over that negative 3. And then we have square root of k times square root of z. Those are different variables, so we're just going to have square root of kz. Now, the inside terms, we have positive 3 square root of z times square root of k. That is the exact same thing, just an opposite sign, which is what we should get. So plus 3 square root of kz. And lastly, we have 3 square root of z times negative 3 square root of z. Now let's look at the coefficients first. So 3 times negative 3 is negative 9. Square root of z times square root of z is z. So just kind of breaking it down into the coefficient and then the radical is going to make these a little bit easier. Kind of like when you had, like if we had 3x squared times negative 3x cubed, you kind of think of these as coefficient times coefficient, and then you look at the x's, kind of like combining the like parts of the terms. Same thing here, you look at the coefficients and then look at the radicals. All right, so now let's see what we can simplify. So on the bottom, as usual, cancel out those inside terms. On the top, there is no way to simplify these square roots, and they're not like terms, so we can't combine them. So on top, we have 2 square root of k minus 6 square root of z. And on the bottom, we can't do anything with the k, and then we have a minus 9z. Again, do not cancel out the k's and the z's. One is a k, one is a square root of k. Also, we cannot reduce the 6 and the 9 because of this subtraction here. So if you think back to chapter 7, when I was putting in parentheses around everything with addition and subtraction, to know that those are stuck together, the same applies here. If there is addition or subtraction next to it, they are stuck together. You cannot reduce these guys. Okay, so let's go ahead and try these last 2 problems, and I will show you when you can simplify them down. So this last set of examples, we're told to simplify. So number one, we're given 24 minus 36 root 7 over 16. Now, first thing you want to check when you're simplifying is, can I simplify any of the radicals? Now, we have a square root of 7 here. That is a prime number, which means we cannot simplify it down. So now what you want to do, and this is kind of like what we saw in chapter 7, I'm going to show you two ways to do this actually, so you can kind of do whichever you prefer. So let me draw this one or write this one down here. So one way to do it is to, thinking about chapter 7, we want to factor and then cancel. So looking at the top here, we can go ahead and factor something out of this 24 and 36. Make sure you only take it out of the numbers in front of the radical, not the radical itself. 24 and 36 are both divisible by 12. So if I take a 12 out, we're left with a 2 minus 3 square root of 7, do not touch the square roots, over 16. And now I can go ahead and reduce the 12 and the 16. So these guys, since there's multiplication right here, the 12 is not in that group of parentheses. I can reduce the 12 and the 16 by 4. So 12 divided by 4 is 3. 16 divided by 4 is 4. So we're left with 3 parentheses 2 minus 3 square root of 7 all over 4. Now, MyMathLab should take this as an answer. If you want to distribute this back in, let me box that one. 3 times 2 is 6 minus 3 times 3 is 9 square root of 7 over 4. That is one way of doing this. The other way, without having to factor, this is the way I like a little bit better, just because when you can avoid factoring in general, it's kind of nice to avoid doing that. So I like to reduce kind of like what we did here, where you reduce down the 12 and the 16, but you have to reduce from every single term. So we have to reduce from the 12, the 36, and the 16. So if we can find a number that goes into all three of those, we can divide each number by that number. And you can always do this twice. It's kind of like reducing fractions, where let's say we reduced it by 2. There is a bigger number that goes into it than 2. So you just want to reduce twice. So if I go ahead and divide all of these by 4, 24 divided by 4 is 6. 36 divided by 4 is 9. 16 divided by 4 is 4. Now, if you notice, we didn't touch anything inside the radicals, and we had to take something from every single term. But we're left with 6 minus 9 square root of 7 over 4. That is exactly what we got over here. So I think this way is a little bit faster. You just have to remember to only cancel out or reduce if you can reduce from every single term, because there are a lot of times when I've seen people reduce just from, let's say, 2 of them, but not all 3. Okay, let's go ahead and try one more of these. This one we're given 2x plus the square root of 32x squared all over 6x. So what do you think the first thing is we have to do with this one? Well, because we have a square root, we want to go ahead and simplify down the square root first, because we can actually simplify it. I can break that the 32 into a 16 times 2, and I'll leave the x squared for now. So we can take out the square root of 16, that's 4. We can also take out the square root of x squared. That's just an x. So we're going to have the 2x plus still in the front. Now, square root of 16 is 4. Square root of x squared is x. Or if you remember the shortcut there, using the kind of divide and remainder rule that we talked about, you take the exponent divided by the index, which is 2. 2 divided by 2 is 1, with no remainder, so there are no x's left on the inside, but there is a 2 left on the inside. Now on the bottom, we have a 6x. And so I'm going to use this other method here that I talked about instead of factoring. You could factor out from the top and then cancel. But if I just go ahead and reduce, make sure you're reducing from every single term, not inside the radical. I can cancel out an x from each of these, so I'll do that first. And then I can reduce the 2, 4, and 6 by 2. So 2 goes into 2 one time, 2 goes into 4 2 times, 2 goes into 6 3 times. Now, this is one that I really want you to be careful with. Notice how I put a 1 here. So we were dividing it by 2. I didn't just cancel out that 2. You want to make sure that 1 is still in the front, plus 2 square root of 2 all over 3. So the way to kind of remember this, because a lot of the times I'll see people put 2 square root of 2 over 3. They just kind of get rid of that 1. That is not right. We need this first term here, because if you take a look at what we started with 1, 2, 3 terms. You should always end up with 1, 2, 3 terms. Unless you added or subtracted something together, which we didn't, you should have the same number of terms that you started with. So keep an eye on that when you're going through and doing these, but that's it for 10.5. Next, we'll see how to solve equations with radicals, and then we'll see those imaginary numbers that I've been talking about.